Hi everyone. I wanted to go over a review for your quiz on Tuesday. I know that our lecture last week was pretty fragmented, and I know a lot of people are nervous about the quiz because there's a lot of information that needs to be covered. But what I wanted to do was provide you with this video to really narrow down exactly what's going to be on your quiz. Everything that I mention in this Echo video is directly related to information coming from your quiz. So this way you don't need to overstudy. The only things I mention in this video will be for your quiz. So please don't overstudy, don't go outside the concepts that I'm going to address. This is strictly to help you because it's so much information and I don't want everybody losing sleep over it. So we're just going to cover it piece by piece. I literally have your quiz next to me, which honestly is more like a test. There's a lot of questions, but it gives you more of an opportunity to do well. And some of it is review and some of it are new concepts that we've addressed in class. So just pay attention. You're welcome to play the video over and over as your studying tool. And if you have any questions, you can certainly email or Remind app message me so that we can figure out what's going on, what questions you have. So here we go from the beginning. Anything I talk about from chapter 1 is literally all I want you to focus on for your quiz. So this is basically the essential concepts of radiologic science that I just want you to pay attention to when you're studying. The first basic concept would be energy, which is the ability to do work. There's different kinds of energy that we're going to address, and you did see all of these slides in class, so I want to just show you this again. So the different types of energy, we have electromagnetic, which deals with X-rays and gamma rays, nuclear, which is your nuclear power plants, thermal energy, which deals with the energy of heat, electrical energy, which deals with how you turn on your lights in your home, how you power devices. Kinetic energy is the energy of motion. So when someone's running, they're exhibiting kinetic energy. Chemical energy can deal with anything at a biochemical level, such as when you eat carbohydrates to give yourself energy, or when you drink coffee, the caffeine gives you energy at a chemical level. And then finally, you have potential energy, which is the stored energy. It's what energy can possibly happen before you start to change it into some kind of other form of energy. Then we need to deal with what is ionizing radiation. So ionizing radiation or ionization is when an electron is removed from an atom. So you have your incident X-ray coming in. It deals with the shells of an atom. So here's your shells, and here's an electron. The electron gets removed from the atom, and therefore it ionizes the atom, changing its energy. So it's changing it to either positive or negative, but it's changing its atomic composition. So it's changing how it's charged. And that's the process of ionization when you're removing an electron. Some more basic concepts are your quantities, your standard units of measurement. Now you can have exposure, which is the exposure of radiation in air, which is measured in Rankins, and there should be a little A here. This is a gray, but there should be a little A right down here to designate what's called an air kerma. You've got your dose, which can be a rad, which stands for radiation absorbed dose, which that occurs in the patient. So when we expose the patient, it's rads. The REM stands for radiation equivalent man, and that's what the occupational worker gets. So that's what we get as radiographers, and that's measured in sieverts. The rad is measured in grays. Radioactivity is something more dealt with in nuclear medicine, but if you have ever heard of a woman by the name of Marie Curie, she's the one who discovered radioactivity, so we honor her by calling anything radioactive. We measure it in curies, or the SI unit would be a becquerel. And then you've got some derived quantities, which volume, mass density, and velocity, which we don't deal with too much in radiography. And then your basic units, which is mass, time, and length. Now here's a very nice chart. It's also located at the beginning of your Bouchon book, so make sure you take a look at that. And this just breaks it down a little bit more clearly. Your exposure, which is your exposure in air. In the US, we call them Rankins, or R. And then SI units, they're air kermas. So there's that little A I was talking about, okay? So that's what an air kerma looks like. Then you've got your absorbed dose, which we talk about the patient, which is in rads in the US, or grays on SI units. Your effective dose, which is the occupational worker, those are in REMS, radiation equivalent man, or your SI unit, which is the sievert. And then you've got your radioactivity again, which is named after our friend Marie Curie, and the SI unit for that is the becquerel. So what are X-rays? X-rays, again, are a form of electromagnetic radiation. They act both like waves and like particles. They're the smallest cluster of electromagnetic energy known as a photon. And then X-rays have a wavelength much shorter than that of visible light. That's important. You definitely need to know the 12 properties of X-rays. You will have to fill that in on your exam. No word banks, no matching, you have to fill it in, so make sure you memorize these. We'll go through them, and it's only going to be the 12 located on this slide, and this slide I did upload for you in the PowerPoint, and we did talk about this slide in class, so you do have it available to you if you wanted it printed out. Number 1, X-rays cannot be seen. Number 2, they have no mass. They are electrically neutral, meaning they don't have a positive or negative charge. They cannot be focused by a lens. They travel at the speed of light, which is 3 times 10 to the 8th meters per second. They are polyenergetic or heterogeneous, meaning they have multiple energies, which moves on to the next one. They can be produced at different energies. They travel in a straight line. They can cause certain substances to glow or fluoresce. They are penetrating. They can be absorbed or scattered, which is your photoelectric or your Compton. Those are important in X-ray. And they can cause damage to living tissue. Give you a moment to take a look at this, and then we can move on. I do want to point out the different energies. So if you have a beam that you as the technologist set at 70 kVp, you can have energies ranging from 0 all the way up to 70 kVp. Anytime you set a kVp, your energy range cannot go beyond that set kVp. So it can't be higher than 70 if you set 70 on your machine. If you set 80 on your machine, it cannot go higher than 80, and so on and so forth. All right, I'm going to move on to the next slide. That's all of Chapter 1, everyone, so don't overstudy Chapter 1. Just going on now to Chapter 2. The structures of matter. Again, we're going back into ionization, which what is ionization? It's the removal of an electron from an atom. Here's your incident X-ray coming in, and it's interacting with an electron of one of the orbital shells. Okay, so ionizing radiation hits the electron is knocked out of its orbit, and then you have ion pairs that remain. You have a positive atom and a free electron. So once this electron is knocked out, this atom now becomes positive, so it's got a positive ionization, and you have a freely floating electron, which this electron can move on and cause interactions with all the different atoms next to it. I wanted to point out your electron shells. The innermost shell, and I made it nice and big for you, no matter what atom we're talking about, the innermost shell is always your K shell. And then as you move outward, it becomes your different letters of your alphabet. So innermost is K, the got L, M, N, O, P, Q, R. It keeps going all the way down. But the innermost shell, again, is your K shell. Now, I'm not going to make you have to know for this exam, this chart inside and out, backwards and forwards. Eventually, you are going to have to know that the K shell, the maximum number of electrons within that shell is 2. You're going to need to know that. So that's for any atom. This applies to any atom that we're talking about, any atomic element. But for your test, I'm not going to make you have to know these. What you do need to know is that the maximum number of electrons, the formula for it is 2n squared. And n delineates your shell number, okay? 2n squared, that's the maximum number of electrons. You need to know this formula. And you also need to know that an atom's binding energy is represented by its shells. Again, an atom's binding energy is represented by its shells, okay? So 2n squared, n equals the shell number. And when we're talking about an atom's binding energy is represented by its shells. Okay, I'm going to go on. Now we're going to talk about different types of atoms and their makeup. So we've got isotopes, isotones, isobars, and isomers. You have to know these. It seems like you probably don't in radiography, but these will be on your registry and these are going to be on your test. So you need to make sure you know these. And there is a nice chart in your Bouchon that addresses that on page 36, table 2-4, which you can look at to help you remember these, but I'm just going to go through them for you. An isotope has an equal proton number. So an isotope has the same atomic number, but different atomic mass. Again, same atomic number, different atomic mass. Okay? Your isotone has equal neutron numbers. So what that means is it has the same number of neutrons, but different number of protons. And I'll repeat that again. Has the same number of neutrons, different number of protons. Then we're going to move down to isobars. So isobars have equal atomic mass number. So same atomic mass, but different atomic number. Again, same atomic mass, but different atomic number, that's your number of protons. And then finally, isomer. So isomers have the same atomic number and same atomic mass, but they're at different energy states. So that's really important. Everything is the same except their energy states. Again, you can refer to that in your Bouchon, page 36, table 2-4, to help you memorize the difference between the isotopes, isotones, isobars, and isomers. I'm going to move on. You definitely need to understand in radiography that there are different types of ionizing radiation. There's particulate radiation, which deals with your particles. That's why it's called particulate. That's your alpha particles and your beta particles. Now, your alpha particles are your least penetrating particles. They can actually be stopped by a piece of paper, so they don't go very far, and they are defined. They are a helium nucleus that contains 2 protons and 2 neutrons. The biggest thing you need to remember, however, is that they are the least penetrating of the particulate radiation. And then you've got your beta particles. Your beta particles, it endures what's called a beta emission, and that releases electrons. So that's the biggest characteristic you need to know for beta particles, that it releases electrons. And your alpha particles are your least penetrating of your particulate radiation. Then you move on to your electromagnetic radiation, which obviously we deal with X-rays. And with electromagnetic radiation, the biggest difference between them is their origin, so where they come from. So when we're talking about gamma rays come directly from the nucleus. Gamma is what you deal with in nuclear medicine. X-rays come from the electron cloud. They come from around the nucleus. So you can get from breaking around the nucleus, which is your BREMS, or you can get from your orbital shells, which is your characteristic. So again, the difference between them is only their origin or where they come from. And there's a nice chart in your Bouchon to refer to these on page 42, table 2-6, which will help you remember, again, the difference and their characteristics. That's page 42, table 2-6. And then here's just to highlight the differences in their sources or origin. So X-rays originate in the electron shells, and gamma rays originate right from the nucleus. Okay, that's all from chapter 2. Moving on now to chapter 3. The reason why we do need to know electromagnetism in radiography is that some of the components of your circuit deal with electromagnetism. It's self-induction, so it rotates because of a magnetic field created by an electric current. And when we talk about electromagnetism, we have to deal with frequency and wavelength, and we have to know the difference between them and wave amplitude. So this slide shows you your wave amplitude. It's basically just how high it goes. So your peak or your crest is the very tip, and your valley is where it drops into the negative portion of the cycle. So it looks like a valley, and your crest looks like a mountaintop. Okay. Now we're going to talk about wavelength. So wavelength is the distance from peak to peak or crest to crest. That's your wavelength. And if you notice, as you look at the different wavelengths, some are wider and some are narrower. Okay? And that can change. So if you double your wavelength, you're decreasing your frequency. So if you're making your frequency or your wavelength longer or wider, your frequency is going to get smaller. See how you've got more of these per unit length versus less. So that's important. If you double your wavelength, you're going to cut your frequency in half. Again, if you double your wavelength, you're going to cut your frequency in half. And here's your frequency. So again, if you look at this slide, I'm going to go back. This is a longer wavelength. This is a shorter wavelength. The longer wavelengths have less frequency. See how there's less peaks? So longer wavelength, less frequency. Shorter wavelength, more frequency. Make sure you know your definition of frequency. So your definition of wavelength, I'm going to go back again, is your distance from peak to peak or crest to crest. The definition of frequency is the rate of rise and fall of a sine wave. So how many times it goes up and down in a given wavelength. Now we're going to discuss the inverse square law. The inverse square law basically is letting you know that as you get closer to a source of radiation, your intensity is going to increase. And as you move further away, your intensity is going to decrease. So the definition is every time you double your distance from your source, you decrease your intensity by a factor of 4. every time you increase or cut your distance from a source in half, you increase your intensity by a factor of 4. So let's talk about that in layman's terms. In layman's terms, what that means is if you get closer to your source, your intensity is going to increase. If you get further from your source, your intensity is going to decrease. So the intensity of electromagnetic radiation is inversely related to the square of the distance from the source. That's a really technical term. You can look at your Bouchon, page 54, and it goes over that. But what you need to be able to do is you need to be able to identify this formula, and you need to be able to plug in your numbers. If you can plug in your numbers and you remember this formula, you will be able to do the inverse square law no problem. And I'm going to give you an example so that we can practice plugging in your numbers. Here's your example. For a given technique, the intensity at 3 feet from the source is 4 millirankin. What is the intensity if you double the distance? So your I1 is going to be 4 millirankin. Your I2 we have to solve for, so we're going to put an X there. Your D1, which is your first distance, is 3 feet. And then the question is telling you that we're going to double the distance. So your D2 is going to be 6 feet. So when we plug everything into, and I'm going to go back to our original equation, which is I1 over I2 equals D2 squared over D1 squared. When we plug everything in, our I1 is 4, our I2 is X, our D2 squared, so our second distance was 6 feet, we square it, we get 36, over our D1 squared, which our D1, or our original distance, was 3 feet. If you square 3, you get 9. When you cross multiply, you're going to get 36x equals 36, and all you have to do is to solve for x, which is 1 millirankin. So the answer to this question is 1 millirankin once you cross multiply your original formula. And then this is going to show you in visual form what that answer looks like. So here's our little sweet puppy dog. We're going to call the dog Winnie because if you can hear my dog snoring in the background, her name is Winnie. So Winnie initially is 3 feet from our source of radiation, and she's getting 4 millirankins. When Winnie doubles her distance and goes to 6 feet, Winnie's only getting 1 millirankin. So this is the visual form of your inverse square law. Okay? That's it for chapter 3. Moving on to chapter 4. Faraday's law. We're going to go through it. You just need to understand it. So you need to understand that unlike charges attract and like charges repel. So unlike charges, positive and negative. So positive and negative attract towards each other, and like charges repel. So positive repels positive, negative repels negative. The electric charge of a conductor is concentrated along the sharpest curvature of the surface. So when something curves, let me draw it. I don't know if it's going to let me. Let's see. See if I can draw something. Yes. So along the sharpest curvature. So there's a curve. I don't know what the zigzag is here, but this curvature here, when it curves, it backs up, right? So everything kind of slows down and backs up at a curve. So that's what this second law is stating. It's stating that it's concentrated along the sharpest curvature. So it's concentrated along here. Now let me go back to my little, let me get rid of that because I don't know why I did that. And then let me go and give you back the pointer if it ever lets me do it. Here we go. Okay, so number 3, electric charge distribution is uniform throughout or on the surface. So your electric charge is going to stay uniform throughout an entire surface. And then finally, the electrostatic force is directly proportional to the product of the electrostatic charges and inversely proportional to the square of the distance between them. Electrostatic force is directly proportional to the product of the electrostatic charges. So you multiply the charges, you're going to get your force. And it's inversely proportional to the square of the distance between them. The further you are from it, the less charge it's going to be. Biggest one you need to know for your test is this first one. Again, the biggest one you need to know for your test is this first one. Unlike charges attract and like charges repel. Ohm's law. Let me get my drawing tool back out. Let's see if I can get it to not do something crazy this time. We're going to use a pen, but I want to do the pen in, if it lets me, I want to do the pen in black. Okay, so Ohm's law is V, which is volts, equals IR, or I times R, and the I stands for your electric current in amps, and your R is for your resistance in ohms. That's why it's called Ohm's law. You need to be able to identify this formula, but you also need to be able to identify it in its different forms. So, okay, bear with me because you know my artistry is awesome. This is going to be a triangle. I know it's a crazy one, but I'm using my mouse, so it's not the easiest triangle to make. So bear with me here. If we put this into triangle form so that it can help you, we're going to put your V up here, your I here, and your R here. So when you take your test, you can draw this little triangle somewhere on your test so that it can help you to figure out the different forms of Ohm's law. So right now you're seeing V equals I times R. But it can also be shown as R equals V divided by I, or I equals V divided by R. Okay, so what you're doing is, and let me go back now to my highlighter. Okay, what you're doing is you're using this little triangle that, I don't even know, it looks like a gnome's hat. But anyway, you're using this triangle to help you determine the other forms of Ohm's law. So this is if you see it on your exam, you can identify it in all its different forms. Okay, and I'm going to leave this up for just a few more seconds so that you can write this in your notes if you're taking notes. But again, this is what you need to know for your exam, and make sure you know it in its different forms. Okay, some symbols that are very important. You need to know them because we deal with circuitry in radiography. So just know your basic symbols: your resistor, your battery, your capacitor, your transformer, and your diode. And you also need to know what they do, but the biggest ones for your exam coming up on Tuesday are these guys, these bottom two. So you need to know what a transformer does. It can increase or decrease your voltage by a fixed amount. And your diode allows electrons to flow in only one direction. And I've talked about this quite a bit in class, but your diode allows you to go from cathode to anode. Okay, so these are your symbols. And we're going to go into them in more detail. Okay, another thing I want to bring up before we move into your circuitry is Faraday's law of electromagnetic induction. So your size of induced current depends on the strength of the magnetic field, velocity of the field as it cuts through the conductor, the angle of the conductor to the magnetic field, and the number of turns of the conductor. The reason why I put this slide up, and it sounds very confusing if you're not really familiar with electromagnetism, but a portion of your generator, or I'm sorry, the portion of your X-ray tube that runs on electromagnetic induction is your anode. That's how it rotates. And your stators help that rotation occur because a magnetic or an electromagnetic field is created when your electrons flow across the tube. So anytime you've got a charged particle in motion, you're creating a magnetic field. And that magnetic field is how your anode rotates. Very, very important. Okay, again, anytime you have a charged particle in motion, it creates a magnetic field. All right. Chapter 5. The imaging system. There we go. Now, there's 3 main components of your imaging system. You need to know them. That's basically your tube, your operating console, and your high voltage generator. In radiography, useful voltages are between 25 and 150 kVp. That's important, meaning anything outside of this range is not going to help us at all in radiography. It's not going to give us the images that we need to see. Tube currents range from 100 to 1200 MA, and that's for basically all the modern tubes that we have. The newer tubes, or the newer generators, I should say, can go up to the 1200 MA. Some of the older equipment doesn't go quite that high. Our equipment runs on 220 volts. That's important. Some of them can run on 110, some of them can go up to 440, but 220 volts is your primary voltage for anything in the United States. And then you've got just some imaging systems that use patient-supported couches. They have to make sure that they have uniform thickness, that they're radiolucent, meaning that you can x-ray through them and they appear clear or black on the image, and they can be floating or motor driven. And if you hear singing in the background, that's my daughter trying to get a snack and she's not being quiet. Jules, shh. Okay, and then here's just again your imaging system broken down. Your operating console allows you to select KVP, your MA, and your time. Your high voltage generator contains your step-up transformer and your rectification system, and also the filament circuit should really be in the high voltage generator section, and then your X-ray tube should stand alone. Your operating console. So this is mostly what your consoles are going to look like. They're digital. You're going to be able to pick the body part. You're going to be able to pick the thickness, which AEC chamber you're using, how thick the patient is, your MA, your KV, all that jazz is located in the operating console. The biggest thing with the operating console is that it's low voltage. That way we can touch it. So occupational workers can touch it without getting shocked. That's super duper important to remember. And here is your operating console broken down. Now, I have said this before and I'll say it again. Everything in your generator, your operating console, it's named for what it does. So let's talk about the line voltage compensator, which down here is where it's labeled. You are going to have to label the entire operating circuit and generator for your quiz. So please make sure that you know this inside and out. Your line voltage compensator uses a meter to measure the voltage provided and a control to adjust the voltage to precisely 220 volts. So in the United States, when it comes from the wall and goes into our unit, it can vary by as much as 5%. So what the line compensator does is it compensates for that variance and makes sure it's a steady 220 coming in. And what your line monitor does is it monitors that incoming voltage and makes sure that it's the steady 220 coming in. The very first component to receive the electric, or voltage, I should say, coming in is the auto transformer. The auto transformer has a single winding and is designed to supply a precise voltage to the filament circuit and to the high voltage circuit. And this also operates on electromagnetic induction. That's what I talked about earlier. So that's why electromagnetism is important to know, because it has to do with several components of our imaging system. So here's your single winding, auto meaning self, so it's self-transforming. It's going to bring voltage up to your KVP section and voltage down to your filament section. Excuse me. These little lines here, those are called your KVP taps. And those KVP taps allow the technologist to pick the precise KVP. Your minor taps fine-tune the major tap selection. So see how these taps are spread further apart than these taps down here. These taps go in tens. So that's if you wanted to do 50, 60, 70, 80, 90, 100, 110, 120, 130. Your minor taps are going 2, 4, 6, 8. So how these would work is if you wanted to set 54, you would pick 50 and then your minor tap of 4. That's how that works as far as major and minor KVP is concerned. Your KVP meter here can also be called a voltmeter depending on what schematic you're looking at, or you might see a large V in this section here. Your KVP meter is placed across the output terminals, see them here, of your auto transformer and reads the voltage. So it's actually reading voltage, not kilovoltage. So that's why it's usually called a voltmeter. The reason why it's measuring voltage and not kilovoltage is because it hasn't been stepped up to kilovoltage yet. So that's very important. So I know Bouchon has it labeled as a KVP meter, and if you put KVP meter on your exam, you will not be wrong. You will be correct, but it technically should be called a voltmeter because it hasn't gone to kilovoltage just yet. When you move down towards the filament end of it, you're going to look at your MAS selector, or your MA selector here, and these are your MA stations. So your 50, 100, 200, 300, 400, 500. That's what's helping pick your quantity, or your MA, your number of electrons. And then up here, you've got your timing circuit. Now, technically speaking, timing should go with MA, but for some reason, when you look at a schematic, usually the timing circuit is placed somewhere in the KVP section. It's always pictured as a box. That's your timing circuit. It allows a wide range of timing intervals to be selected. MAS timers can terminate the exposure when the desired MAS has been obtained. Those MAS timers are talking about your AEC, or your automatic exposure control. You can also use fixed techniques and pick your times that you need. So if you wanted a faster time for like a pediatric patient or somebody who has Parkinson's and you don't want a lot of motion, then you would pick a faster time than if you had someone who could hold still. So that's your operating console, all low voltage. Everything labeled on here, you need to be able to label on your test. And then I'm going to move on. Your high voltage generator. Now, usually in the room, you'll see it looks like a little box. We want to stay away from that. It's high voltage. We don't want to touch it, so that way we don't hurt ourselves. There's 3 primary components of the high voltage generator. You absolutely need to know them. So that's the high voltage transformer, or your step up transformer, your filament transformer, which is your step down transformer, and your rectifiers, which your rectifiers change the current from alternating to direct. What the high voltage generator does is it increases the output voltage from the auto transformer to the necessary kilovoltage for X-ray production. So it changes your volts to kilovolts. Your high frequency generators are more commonly used in today's imaging departments. Anything with DR or CR is high voltage or high frequency. You really won't see the other forms of generators anymore unless you went to other countries or maybe some rural areas or even some older doctors' offices. High frequency generators are full wave rectified, meaning it swings that negative portion of the waveform up into the positive end. So let me draw it again so that you can remember. And I know you love my drawings, so here we go. So here is your line. Positive is up, negative is down, and here's your waveform. Positive side, negative side, positive side, negative side, positive side, negative side. So when it says full wave rectified, it takes this negative portion and swings it up. So dot, 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 dot. So you're using all of the waveform, okay? So all this gets swung up here and you end up using the full waveform. So it's fully rectified at 60 hertz, and then it's converted to 500 to 25,000 hertz. And these high voltage generators are much small, or the high frequency generators are much smaller than the high voltage generators. So the high voltage ones look like almost like a standing wall unit, and the high frequency ones are a little box. Okay, here comes the high voltage circuit. This is the no-no. We don't want to touch this at all. You are going to have to label this as well, so please pay attention. The high voltage circuit contains the filament transformer, which is down here. It's a step down unit. So you see how you have more windings on the primary side and less windings on the secondary side of your transformer. So it looks like a step going down. It steps down the transformer, it steps it down, the voltage, excuse me, from 150 volts down to 12 volts. So 150 to 12. And your amperage is changing. Your amperage is going from 0.5 to roughly 5 or 1 to 8 in that area there. Okay, so it's stepping it down. You've got an MA meter here. It can also be called an ammeter, and it looks like a big A in there depending on the schematic, and it's basically measuring your tube current or your milliamperage. Then you've got your high voltage transformer, which is up here. It's stepping it up, meaning you have less windings on your primary side and more windings on your secondary side. So it's changing the voltage from volts to kilovolts. So here's where the magic happens. You've got volts on this side and it goes to kilovolts on the second side. And the amperage also goes from amps to milliamps. Okay, so this is where your volts go to kilovolts and your amps are going to milliamps. And then here are your rectifiers. You can see the diodes here and your voltage rectification. And what it's doing is, what does a rectifier do? Or what does it mean to rectify? It means to make it right. So what it's doing is it's making the alternating current into a direct current, because we need a direct current in order to operate our X-ray tubes. It has to go from cathode to anode. It can't go back and forth. And it's also very important down here, this little fact, that in the United States, an alternating current goes through a complete cycle every 60th of a second. And I'll repeat that. An alternating current goes through a complete cycle every 60th of a second in the United States. Very important. And then this little symbol here, which I pointed out before, that's your ground. That makes sure that your tube doesn't blow up, basically. Okay. Next. Those diodes that I pointed out in the rectification circuit, this is what a diode looks like. You've got your triangle here. And what you need to know as radiographers, it's very important that you need to know that the current flows with the point and the electrons are going to flow against the point. So your negative section or your cathode section of your solid state semiconductor, your diode, which is your X-ray tube, your electrons are going to flow from cathode to anode, and your current is going to go from anode to cathode. Okay, super important. So an electronic device that contains two electrodes, positive oh no, something's wrong with my mouse. Here, positive to negative, and ensures that electrons flow from cathode to anode. And it's essential for these diodes for safe and efficient tube operation. So we need to make sure we have these diodes in the rectification circuit in order to make sure that our alternating current becomes a direct current. And I'll leave this up for a second so you can just write it in your notes if you need to. Moving on. And here is your entire schematic. This is what you will have to label. I'm using the exact same picture. It's not going to change, so it would be in your best interest to remember this. Here we didn't talk about too much, but the focal spot selector. The focal spot selector allows you to choose your large or small focal spot. Small focal spots are used for fine detailed bone work, and your larger focal spots are for larger body parts. This is part of your labeling. Everything needs to be labeled where it is. So nothing's going to change. It's not going to throw you any curveballs or anything. You need to know which section is your operating console, which section is your high voltage, and then which section is then your X-ray tube. Okay? Gonna leave this up for a second, and then I'm gonna move on. This is available to you in the PowerPoint that I uploaded for you, so if you printed out the PowerPoint, you can practice this as well. And then this just breaks down the sections again, what's located in each section. You can take a look at it real quick. We've already gone over it, but just so that if you'd like to write this down in your notes. I do believe this is also in the PowerPoint I provided you, so I'll give you a second to write it down. Okay. I know we also talked about voltage waveforms in class and talked about voltage ripple. And that's the rippling. I'll show you the next slide real quick just so that you recall what we were talking about. The voltage waveforms is the rippling as it goes through the cycle, and the cycle is every 60th of a second in the United States. Very important again to remember that. Let me go back now. So for single phase units, you have 100% voltage ripple because it's only half rectified, or meaning you're losing most of your technique that you've originally set. Single phase units no longer exist in the United States. Well, they shouldn't anyway. They should have been taken out of all the facilities because they are not ALARA compliant, because you have to double and sometimes triple your technique in order to get a proper exposure. So they have 100% voltage ripple. They are the least efficient of all the generators. And then you've got other generators. You've got 3-phase 6-pulse, 3-phase 12-pulse, and 3-phase, well, this should just be high frequency, really. With these, you've got to remember your different numbers for your voltage ripple. So 3-phase 6-pulse is going to be 14%. Your 3-phase 12-pulse is going to be 4%. And then your high frequency units is less than 1%. And now let me move on to the next slide so that makes a little more sense to you. Here you go. Half-wave rectified. So these guys are your single phase generators. 100% voltage ripple. Bump, bump, bump. It's not using a lot of your technique that you've set. And with the half-wave rectified, you lose the whole negative portion of your cycle. So it's really a waste and you're just over-radiating the patient. Your 3-phase, meaning that it's going 3 times through your 60th of a second cycle, 6 times. 3 times through your 60th of a second cycle, 6 times. Okay, so moving on down here, you've got 3 times, it's going to go 12 pulses per cycle. Then down a little bit further, see how nice and almost straight of a line this is? That straight line there, it's less than 1% voltage ripple. It's very calm, and this is the most efficient of all the generators because you're getting the technique that you've set as you're going along. All right, I'm going to give you a second to write that down. I also want to just go back. Let's see. I guess we could use this one. When you're looking at the full wave form here, I want you to understand, again, in the United States, it's a 60th of a second, and you've got your full wave rectified units. If it's full wave, it's using both sections of the cycle. So 3-phase units, they go 3 times through the cycle. So 3 times 60 is 180. And when you're using a full wave, you're multiplying that 180 by 2 because you're using both the positive and negative swing of the cycle. So with 3-phase units, you're going to end up getting 360 pulses per second. Again, 3-phase units, 3 times the 60th of a second, which is 180, and you're using the positive and the negative portion of the cycle, so you're going to multiply your 180 times 2. So anytime you're using those 3-phase units, you're getting 360 pulses per second, making them a little bit more efficient than your single-phase unit. Okay? And actually, let me draw that out, because sometimes saying it is a little bit more confusing than drawing it. So again, full wave uses both the positive and the negative portion. So see how this negative portion is swung up? So it's used up here. So with any type of 3-phase unit, you have 1/60th of a second, okay, going 3 times. So what you're going to do is you're going to multiply the 3 phases times 60, which equals, why does that do that? Whatever, 180. All right. And then that's on the positive side. But when it's fully rectified, you have to include the negative side. So you're going to do that 180, because it's fully rectified, times 2, which equals your 360 pulses per second. And I hate that it does that line, but anyway. So just so that you can see that out, full wave rectified, you use both sides of the cycle, so you have to multiply it times 2. 3 phases goes 3 times through that cycle, so 3 times 60 equals 180, times 2, which is your positive and your negative swing on your cycle, so 360 pulses altogether. Moving on. Chapter 7, X-ray production. There's a lot more information in this chapter than the prior chapters, just to let you know. X-ray production. 3 things need to happen. We've gone over this from the beginning. Let me get my little highlighter again. Come on. Okay, 3 things need to happen. We need thermionic emission, so electrons need to be boiled off. That's coming from the filament side or the cathode side. They need to be set in motion. So your voltage pulls your amperage across the tube, and then they need to be suddenly stopped, and that's usually when they hit the target. Those are the 3 things that need to happen in order for an X-ray to be created. Now we're going to talk about the tube. This, you also have to be able to show, I don't know what all these little numbers and things are here, but anyway, sorry about the picture being a little skewed, but this is what you're also going to have to label, same picture for your test, okay? So your anode, which is the positive side. This is actually the rotor, so it's what rotates your anode stem. These are your stators that operate on electromagnetic induction, and that's what rotates your anode. Here is your actual target, which is a tungsten disc usually coated with rhenium. Here is your cathode side, your negative side of the tube. This is where your electrons are going to get boiled off. And here is the filament inside the focusing cup. So the filament always looks like this squiggly line here that's also made of tungsten inside your focusing cup. This is the port or the window where the x-rays are going to come out. And all of this is enclosed in a very nice glass envelope. So all of these things you need to be able to label on your exam. Please make sure you study that. We've also talked about interactions at the target. So with interactions at the target, you're going to have two. You're going to have Brems or Bremsstrahlung, which means the breaking of the electrons around the nucleus, or you're going to have characteristic, which characteristic deals with your orbital electrons and your shells, okay? So back to Brems. It's a breaking of the electron around the nucleus. Energies below 70 kVp comprise 100% of the beam. Above 70 kVp, 85% of the beam is Brems and 15% is characteristic. Your characteristic is characteristic of the target element. The one we care about in radiography is tungsten, and the K characteristic or the K shell. The K shell has a binding energy of 69 keV. So that's important to remember, 69 keV for tungsten, K shell. During the ionization process, the process of changing the charge of an atom by removing an orbital electron, which is removing that K shell. Characteristic X-rays get emitted when an outer shell electron fills that inner shell void. So when you knock out your K shell and your L shell or a different orbital shell drops into the K, that exchange in energy creates your characteristic. And again, energies above 70 kVp comprises 15% of the total beam. That's because you need at least 70 to knock out the K shell, because the K shell has a binding energy of 69 keV. So you need at least 70 to knock it out. Give you a second to write it down. This slide is also available on your Blackboard. And I'm going to keep going. And this is what characteristic looks like. So your incident comes in, this is your electron coming in, interacts with an inner shell. When that interacts, what happens is you get the K shell electron gets booted out, and that exchange in energy from another shell trying to fill its orbital space creates the characteristic X-ray. And here's your Brems. So your Brems comes in, swings around the nucleus, and this exchange in energy, changing the direction of the projectile electron, causes a Brems X-ray. This one is low energy because it's not quite a sharp curve, so you need less energy exchange through this area. The sharper the curve, the more energy exchange has to be made in order to change the direction of the projectile electron, so you've got a higher energy Brems here. This is just showing you your emission spectrum. Now, when you see a nice hump here, that's the continuous emission spectrum, and when you see a straight line, that's the discrete emission spectrum. The reason why it's discrete is because it's finite. It's telling you exactly what energy or how many X-rays are coming from specific orbital shells, whereas your continuous here is telling you how much Brems is coming out. And I'm going to show you a better picture of this in 1 second. Here's when you put it all together. So this MO stands for molybdenum, or Moly for short, and this W actually means tungsten. Tungsten is called Walum, or Wolfram, I think, and that's why it's delineated with a W. So when we're talking W, we're talking tungsten. When we're talking MO, it's Moly. And it's showing you the different quality and the different quantity of the X-ray beam for each specific target element. So when we're talking about tungsten, tungsten has a higher quality beam. So higher quality is always shifting to the right. Lower quality is always shifting to the left. So that's why the moly here is shifting to the left, because it's low quality. And that's why your tungsten is shifting to the right for its characteristic X-rays, because it's higher quality. Now when we talk about the BREMS portion of each of the elements, this continuous spectrum here is dealing with your amplitude, and you see how the hump is a little bit more to the left, meaning it's not a lot. The quantity or your amplitude is not very high, so there's not a lot happening there, and it's not as good a quality as the tungsten element. And then if you look at the tungsten element, you see how the hump is starting to shift over now to the right, and it's a much higher amplitude, so the quantity is much more. So quality is left or right, high quality goes right, low quality goes left, and the quantity is your amplitude or your up and down. And this is visually showing you how certain factors affect your emission spectrums. So when you're doubling your MAS, if you notice here, your amplitude doubles. And then on the discrete spectrum, your line doubles. When you increase your KVP affects both your amplitude and your position on the emission spectrum. So when you increase your KVP from 72 to 82, your amplitude is going to go up, but not proportionally, and your whole spectrum is going to shift to the right because it's going for better quality. So KVP affects amplitude and position. MAS only affects amplitude. Filtration also affects both amplitude and position. It's inversely affecting it, but not proportional. So, well, that's not true. It's inversely proportional, I guess I should say. When you add filtration, so you start at 2 millimeters of aluminum and then you add 4 millimeters of aluminum, it's going to cut your quantity in half, but it's going to make it a higher quality beam. So when you add filtration, you decrease quantity, but increase quality. And that's because you're removing the low energy X-rays from the beam. So again, when you add filtration, you decrease quantity and increase quality. When you remove filtration, you're doing the opposite. You're increasing quantity, but you're adding those low energy X-rays back to the beam, so then your quality will then decrease. And then as far as voltage generation, that deals with your generators, your single phase, your three phase, and your high frequency. Single phase is the least amount of quantity and the least amount of quality. Three phase is kind of in the middle. And then high frequency has the most quantity or highest amplitude and the best quality. And now I'm starting to lose my voice a little bit, so I apologize. I'm going to try and keep going through this as best I can. Here's a nice chart that kind of breaks down what I just said to you. I'm going to leave it up for a moment for you to write into your notes. I do believe this is also available on the PowerPoint I uploaded online, but just if you need to rewrite it, I'll give you a few moments. Okay. 15% rule. You are going to have to do a math equation for this, so please pay attention to the 15% rule. For an increase of 15% in KVP, it's equivalent to doubling your MAS. I gave you an example of a math equation that you might see on a test or even on your registry when it comes time. So for a technique of 100 kVp at 20 MAS, it yielded an image that was not well penetrated but had good optical density. What would you do to fix the image? With this particular equation, what you'd like to do, since it's well penetrated, or I'm sorry, not well penetrated, but the optical density is good, you would want to increase your penetrability. And I just have to pause this for just 1 second because my son came home and I know he's going to be loud. So give me 1 second here just to pause this. Okay, I am resuming. I instructed my son to stay in his room and be quiet. Oh no, hold on. I have to go back now and find the slide we were on. Let me make my life easier. We're on slide 40 something. Nope. Nope. Okay. All right. So again, 15% rule, a technique of 100 kbp at 20 MAS yielded an image that was not well penetrated but had good optical density. What could you do to fix the image? Well, you can increase the kbp by 15%. In order to increase your kbp by 15%, all you have to do is multiply the number times 0.15. And with, I used an easy one, 100. So 100 times 0.15 is 15. So you add 115 to it to get 100, or you add 15 to it to get 115 kbp. And then in order to maintain your optical density, because your example is telling you that the optical density was good, you're going to need to cut your MAS in half, because increasing your kbp by 15% is equivalent to doubling your MAS. So you don't want to make it 2 times as dark. You want to keep your optical density the same. So in this particular equation, you're going to increase your kbp by 15% and you're going to cut your MA in half. So the answer would be 115 kbp at 10 MAS. Give you a second to write this down in case you need it. Okay, here's a second example. A technique of 100 kbp at 20 MAS yielded an image that was well penetrated, but the image was too light. What could you do to fix it? I think I might have screwed this up for you guys. You can increase your kbp by 15%, but really all you need to do is double your MAS for this particular equation. This is a bad equation. I'm going to actually move past this because I don't want you guys to read this. I think I screwed that up for you guys, so I'm just going to move on. But whenever you need to change the penetrability or keep the penetrability the same but change your density, if it's your density, you just want to adjust your MAS. If it is not penetrated and too light, you want to change your kbp and keep your MAS the same so that it doubles. I could maybe load another example, but you need to read about your 15% rule. You need to be able to apply it when you're taking your test. Moving on to interactions with matter. Actually, I really want you to do this. Hang on, we just got to fix this. So here's what I'm going to do. I just need to erase something, or mark it out at least. Okay, so what did I do that for? Okay, anyway, no, we're going back a section. Okay, for the second example, instead of it saying it was well penetrated, it's not well penetrated. So let's get rid of this. Oh my goodness, I'm a hot mess. All right, I gotta fix this for you guys. This is all I really need to do. It is not well penetrated. And the image is too light. Okay, so it's not well penetrated and the image is too light. So let me put this here. Not. Okay, now I feel better. Okay, so let me read this again. Sorry, I'm making you probably crazy. A technique of 100 kVp at 20 MAS yielded an image that was not penetrated and the image was too light. What would you do to fix the image? So what you would have to do with this particular equation is you would have to increase your kVp by 15% because it was not well penetrated, and you would keep your MAS the same. Because when you increase your kVp by 15%, it's equivalent to doubling your MAS. So you have to keep your original MAS when you increase your kVp by 15% in order to darken your image. Again, it's not well penetrated and the image is too light. So in this particular case, you would increase your kVp by 15% and you would keep your MAS the same. Why? Because you want your image to be darker, and if you cut your MAS in half, you would be keeping the optical density the same instead of making the image darker. And I'll leave this up for you so that you can write it down correctly since I messed it up on the slide. And I'm going to keep going in just a second. Now we can move on to interactions with matter. And I'm going to have to just pause one more time because my daughter wants to ask me a question. So hold on. Okay, and I'm back. Chapter 9, interactions with matter. We're almost there, guys. My voice can't take much more anyway, but your basic interactions with matter, your coherent, which can also be called classical or Thomson, and that we don't really care about. It's just scatter. It occurs at energies of 10 keV. Your Compton, which is also scatter. Your photoelectric effect, which is an all or nothing. Pair production, which is used in PET imaging, and its total weight or energy is 1.02 mega electron volts. And then you've got photodisintegration, which results in a nuclear fragment, and that is usually in like industrial stuff or major science experiments, and that occurs at energies of 10 mega electron volts. Here's just an image of coherent scatter. Your incident comes in, scattered X-ray comes out. Again, it's low energy, 10 keV. Now here's your Compton. Compton deals with outer shell electrons. Your incident comes in, it interacts with the outer shell electron, gets it all excited, makes heat. So this is where your heat is getting created. That's your 99% heat happening. Okay? Makes heat from outer shell excitation. Ejects a Compton electron. And during this energy transfer, creates a scattered X-ray. And here's your angle of deflection. Now, the angle of deflection can occur at any angle. So 0 to 180, any angle. If it comes right back at you, it's got more energy than if it kept going. If it keeps going, it means the ball can't hit the wall, so the ball just keeps going and there's no energy transfer. So it can occur at any angle. Remember that. Very important with Compton. Photoelectric, again, is an all or nothing, and this is a really good representation of that. Your incident X-ray comes in, it gets completely absorbed by the inner K shell, and a photoelectron gets knocked out. Complete absorption. That's your photoelectric. That's how you get your bone on your image, your different shades of grays on your image. It's because of the absorption right there. Then you've got pair production, which occurs in positron emission tomography. It's where you are getting two electrons. One is a positron, so a positively charged negatron, or a positively charged electron, and a negatron, which is a negatively charged electron, both coming in at 0.51 mega electron volts. And because there's two of them, the total energy for this type of interaction is 1.02 mega electron volts. Photodisintegration is your nuclear fragment. That's when an incident X-ray comes in and literally pushes out a portion of the nucleus. And that usually is nuclear bombs, things like that, stuff we don't want to mess with. And that occurs at energies of 10 mega electron volts. Now we're going to move on to the concept of differential absorption. Differential absorption deals with Compton scatter, photoelectric absorption, and transmission. You need to know that differential absorption deals with those three things: Compton scatter, photoelectric absorption, and transmission. And you see how this Compton scatter is jumping off the patient? This is what we usually get as our dose as occupational workers. It's from the Compton scatter coming off of our patients. Here's some factors that affect differential absorption. Higher atomic numbers absorb better. So with photoelectric absorption, the photoelectric absorption is greater in absorbers with higher atomic number, meaning bone has a higher atomic number than fat. So bone is going to absorb X-rays more so than fat would. Compton scatter is unaffected by the atomic number. So it doesn't matter how thick or how heavy the item is that you're imaging or the tissue is that you're imaging, Compton isn't affected by that. When you increase your KVP, so you're making it a higher penetrating beam, so it's going to higher quality, it's going to go through the patient better, your photoelectric absorption decreases and your Compton scatter remains proportionally greater. So again, your absorption is going to be less because your KVP is higher penetrating, so it's going to be able to go through the patient more, but your Compton is going to be considerably greater. That's that 40 keV crossover I was talking about. And then increased mass density, so the heavier the patient or the thicker the tissue, your photoelectric absorption is going to increase, and so is your Compton, because it's just more atoms to work with or more molecules to work with, so that's why everything increases. I'm going to leave this up so you can take a note. Again, this is also available in the PowerPoint, I believe, on your Blackboard. And then this is a nice chart that just kind of breaks down exactly what I was just talking about. So differential absorption deals with photoelectric absorption, Compton scatter, and transmitted X-rays. Those three things are required for the differential absorption process. And this deals with the patient, okay? The next concept is talking about attenuation. And attenuation is a weakening of the beam as it passes through matter. So it's the reduction in the number of X-rays as the beam passes through matter. What it's affected by: thick tissue. Approximately 50% is lost for every 4 to 5 centimeters of tissue. So as your patient is thicker, or the body part that you're imaging is thicker, for every 4 to 5 centimeters of that tissue thickness, you're losing 50% of your original beam. So at that point, your beam starts at 100 above the patient, and then as it goes through the patient, as it goes through every 4 centimeters of tissue, you're already down to 50%. The tissue type. So as the atomic number is increased, your beam attenuation is increasing. Again, that deals with the atomic number of bone versus the atomic number of fat. Bone absorbs more than fat, so therefore your beam is going to be weakened more going through bone than it would be through fat. Mass density, how large or small the body part is that you're imaging, and again, the beam quality. So the higher the KVP, the higher quality beam you have, the more penetrating it is. You're going to have less beam attenuation because the beam's going to be able to go through the patient more. And I'll give you a minute again if you need to write any notes on this. So beam attenuation is the product of absorption and scatter. What's absorbed and what's scattered off. And then the remnant radiation, of course, I talk about this all the time in class. I've mentioned it several times. Out of everything that happens, 99% of your initial, of your electron interaction, your X-ray beam is converted to heat. 1% of it is your actual beam. And out of that 1%, 0.5% of it is going to actually attribute to your image. So 99% of it gets absorbed and scattered off, 1% gets through the patient, and 0.5% of that actually makes the image. Remember that, 0.5%, not 1%, 0.5% makes your image. And I believe that's it, ladies and gentlemen. Let me double check. Nope, one more slide, last one, I promise. So this is just showing you what I've been talking about as far as absorbed and transmitted. Anything absorbed is going to be your different grays, your whites, things like that. Anything transmitted through the patient, meaning the KVP penetrated through it, is going to show up black or darker. There's your lungs, which show up black, or air in the bowel, air in the tummy, that's going to show up black. And then different atomic or anatomic tissues of varying densities are your shades of gray in between. And that's how you get your image. So that is it. I'll go back to that so we don't have to stare at a black screen. It's a long test, but again, it gives you a lot of opportunity to do well. Everything I talked about in this video is absolutely 100% what's going to be on your test. Do not overstudy. Just go over what I talked about in this video. Make sure if you have any questions, you address it over the weekend or on Monday. You can email me or send me a remind if there's anything you need to know. And I think everybody's going to do fine as long as you follow this video and as long as you study just what I've asked of you. That way you're not going to overstudy and confuse yourselves. I really hope this video helped. I apologize for the way things have been so fragmented, but we're going to get there. We're going to get everything organized, and I think these kinds of videos before your tests are going to help you. So again, I hope this helps. I'll see everybody on Tuesday. Enjoy your weekend, and just breathe. Everybody's going to do fine, I promise.